Hi, we've been looking at designing optical fiber sensors for various applications using different properties of light. We started looking at amplitude modulated sensors, then went on to look at phase modulated sensors, and lately we've been looking at wavelength modulated sensors. So now it's time to move on and look at the other characteristic of light that describes light, which is polarization. So we'll look at what can we do by looking at changes in polarization, whether that could be used for picking up certain perturbations. That's what we will discuss in the next couple of lectures. So we're talking about polarization modulated sensors. Right, and as usual, we start with an optical source, and of course we want to look at the output, light output, using an optical receiver. And let's say we have a fiber optic sensor that we are trying to make. So when light is propagating through this optical fiber, you can describe that light in terms of different quantities, like specifically in terms of the electric field of corresponding to that electromagnetic wave. And previously we saw that the electric field is a vector that can be expressed in x, y, z, and there's those spatial coordinates and then time. So we said it has a certain amplitude, and then you have a e power j omega t minus beta z term. So omega corresponds to the frequency, the angular frequency, and beta z corresponds to the propagation phase. And now we are ready to look at this other aspect, which is the polarization of the light. When it comes to polarization of light, let's actually talk about modeling the fundamental mode as a plane electromagnetic wave. And if we do that, then if propagation is along the z direction, let's say this is our z direction, then we are now looking at the wave having polarization components in the transverse plane, that is actually in the xy plane. So in general, instead of just having some common amplitude, you can talk about the amplitude in the x direction and the y direction. So you can talk about let's say ax ex plus ay ey, right? And let's just say that in general there is no rule that the x and y components have to be in phase. So there could be a difference in phase between the two components, and that's what we are denoting by e power j phi. So that can potentially describe the polarization of the wave, right? It could be either oriented in the x direction or in the y direction or somewhere in between, and it might actually have a phase difference relative to each other. Okay. However, in terms of picking up, so how can we use this as a sensor? Well, whenever we perturb the fiber, whenever we expose this to perturbations, right? These perturbations can change the polarization of the light. Okay, so by monitoring that change in polarization of light, you could possibly say something about the perturbations, specifically quantify the perturbations. Okay, so we'll come back and look at what type of perturbations that are quantifiable by looking at changes in polarization. But what we know is that the optical receiver, the photodiode as part of the optical receiver, which is the front end of the optical receiver, is not polarization sensitive. So it cannot actually tell if there is a change in polarization. So just like how we dealt with this situation with phase modulated and wavelength modulated sensors, in polarization modulated sensors, we need an optical demodulator, right? So an optical demodulator which can convert changes in polarization to changes in intensity, and then that can be picked up using our optical receiver. Okay, so we will look at what this optical demodulator is all about, but let's start looking at polarization. What is polarization? Well, polarization can be defined as the evolution of the electric field orientation So light is an electromagnetic wave, so the electric field corresponding to that, the orientation of the electric field during propagation is what we are tracking as far as polarization is concerned. Now, you may ask the question, why is it an electric field? Can I do that with a magnetic field? Sure, you could use either, but the convention is that we go with tracking the electric field, and we do expect that the magnetic field is oriented in perpendicular to that electric field. Okay, so you can of course do the same with respect to the magnetic field if you want. Okay, but we are looking at evolution of the electric field orientation during propagation. So we talk about, see, if a wave is propagating towards you, now you can look at the wave as being having a certain electric field, and how that electric field is evolving as a function of time is what we are, as it propagates, is what we are actually tracking. Okay, of course it could be like this, or it could be bouncing like this, or it could be bouncing like this, or it could be rotating like this as it's coming towards you, right? So that all these actually constitute different states of polarization, and like I said, what we are looking for as far as polarization modulator sensors is concerned is that these states of polarization are changing and corresponding to a certain perturbation that it's exposed to, that the material is exposed to. Okay, so the key thought that we are going to rely on, and this is something that is probably inherent in the way we have expressed, is the fact that any polarization state may be expressed as just say expressed in terms of two orthogonally polarized components, right? So what are we talking about? Well, we're talking about, in this case, for example, we are expressing in terms of the x component and y component. So the AX is actually a linear polarization component along the x direction, and AY corresponds to a linear polarization component along the y direction. So we could express any polarization in terms of two orthogonal components. So we are in this case saying that the two orthogonal components can correspond to these two linearly polarized components along x and y directions. Okay, and of course it could it could also have with a phase change between them. So in this case, this quantity within the brackets, this actually denotes the polarization, and it could be any arbitrary polarization state. Okay, so that's the beauty of this. Any arbitrary polarization state can be expressed in terms of these x and y polarization components. Evolving as a function of time is what we are, as it propagates, is what we are actually tracking. Okay, of course it could be like this, or it could be bouncing like this, or it could be bouncing like this, or it could be rotating like this as it's coming towards you, right? So that all these actually constitute different states of polarization, and like I said, what we are looking for as far as polarization modulator sense is concerned is that these states of polarization are changing and corresponding to a certain perturbation that it's exposed to, that the material is exposed to. Okay, so the key thought that we are going to rely on, and this is something that is probably inherent in the way we have expressed, is the fact that any polarization state may be expressed as just say expressed in terms of two orthogonally polarized components, right? So what are we talking about? Well, we're talking about, in this case, for example, we are expressing in terms of the x component and y component. So the AX is actually a linear polarization component along the x direction, and AY corresponds to a linear polarization component along the y direction. So we could express any polarization in terms of two orthogonal components. So we are in this case saying that the two orthogonal components can correspond to these two linearly polarized components along x and y directions. Okay, and of course it could it could also have with a phase change between them. So in this case, this quantity within the brackets, this actually denotes the polarization, and it could be any arbitrary polarization state. Okay, so that's the beauty of this. Any arbitrary polarization state can be expressed in terms of these x and y polarization components. And your y component may be it has got the same frequency and same phase. So, but it might have a different amplitude. So, your y component might be something like this, right? It's evolving something like this. So, this is Ey and this is your Ex component. Okay. Now, to look at the actual polarization of this, you want to look at the wave as it's coming towards you. So, you define let's say the xy and let's say the z is the direction coming towards you. So, this has got to be x and this has got to be y. So, what we are saying now is Ex is actually having a certain amplitude. So, Ex you can represent as having this much amplitude, but Ey is not having as much amplitude. So, you say Ey is something like this. So, then when we look at the combination of that, and both are actually in phase. So, when you look at the combination of that, combination would probably look like something like this. So, this is actually combined. When you are looking at this together, they are combined oscillating in a orientation like this as it's propagating along this z direction. Okay. So, this is the polarization, and this actually describes a line, right, as it's propagating. So, this is actually what you call as linear polarization, right, and that actually makes an angle theta with respect to the x-axis, where theta can be defined as tan inverse of Ey over Ex, right. So, of course, if you have only x component, then Ey equal to 0, then theta equals to 0, and in the other case where you have Ey is present and Ex is 0, then that corresponds to theta equals to pi by 2. Okay. So, that is actually linear polarization, which could have any arbitrary orientation in this transverse plane. Okay. Now, let us move on and let us look at case 2. So, I would still like to retain this. Case 2 is what if phi equals to plus or minus pi by 2. Let us actually look at the case of what if phi equals to plus pi by 2. So, in this case, and let us say Ex equal to Ey, right. Now, in this case, we are saying that Ey is actually leading with respect to Ex. So, if we plot a similar picture with respect to time, right. So, so what we are saying is Ey is leading with respect to Ex. So, Ey is something like this, and Ex now is going to come like this. Ex is going to evolve like this, and both are actually we are saying is having equal amplitude. Okay. So, this is your Ex and this is your Ey. So, now let us look at what happens as far as your combined polarization is concerned. So, once again we look at the x, y, and this is z, right. So, if you look at the polarization and that it's how it's evolving with respect to time. So, initially the maximum at time equal to 0, the maximum is along the y direction, and or maybe I should draw the combined polarization. So, initially it's at it's got a maximum at y direction, but after a certain time y goes to 0 and x is actually present. So, it goes from basically here to here, and then after some time your y goes to maximum, x goes to 0. So, it goes here, and then after some time it goes to maximum of negative x, and then it goes back to its original thing where y is maximum and x is 0. Okay. So, this is this repeats itself as it propagates in space, and of course, with respect to space you can say that this is repeating itself with a wavelength lambda. Now, this actually constitutes what is called clockwise, and it's actually defining a circle here. So, it's called clockwise circular polarization. But to define it, you have to use your left hand. So, you have your thumb pointing the direction of propagation, and then you're sweeping it in the clockwise direction to define this. So, so this is also called left circular polarization, right. So, this is left circular polarization. Now, if we had started with the case if phi equals to minus pi by 2 and Ex equal to Ey, you would have essentially seen something slightly different. In that case, Ex, it would have started with maximum of Ex, and then it would have gone started with maximum of Ex, and then it would have gone to maximum of Ey, right, because in this case Ex is this component, and then Ey would be lagging Ex. So, Ex would replace the blue, Ey would replace the blue curve here, and so it goes like this, and then it goes like this, and then it goes like this. So, this is called counterclockwise polarization, or in other words, it is also called as right circular polarization, because what we are using in this case is your right hand. So, you have this thing pointing along the direction of propagation, your thumb pointing along the direction of propagation, and you are using your right hand to describe the evolution of the polarization, right. So, so this is called right circular polarization. But in any case, if we have phi equals to plus pi by 2 or minus pi by 2, but E is equal to Ey, this is called circular polarization in general, right, because it defines a circle. Now, if Ex is not equal to Ey, or if phi is not equal to plus or minus pi by 2, in any of those generic cases, you say case 3, phi is not equal to plus or minus pi by 2, or Ex is not equal to Ey, you would find that this is actually defining a ellipse. Okay, so this is what you would call as elliptical polarization. Okay, so there is actually a neat way of representing these polarization states, that is whether you say linear or circular or elliptical, and that representation in a three-dimensional way is through what is called a Poincare sphere. Okay, so it's named after this famous scientist named Poincare, right? But essentially he found a very nice way of representing this. He basically defined one axis like this, and so he basically defined it as a three-dimensional sphere. All these different, he found that was actually a convenient way of representing this. Now, of course, I am not drawing it as a three-dimensional sphere, but I can explain to you what it essentially means. But essentially this sphere over here, which you can probably imagine in terms of 3 dimensions, you say, okay, this is, if you are looking at the depth of that sphere, that's what it corresponds to. The top of the sphere is your right circular polarization, and your bottom of your sphere is your left circular polarization, and this one is your linear horizontal polarization, and this is your linear vertical polarization, right? So, we know what these polarization states are. This vertical polarization corresponds to this horizontal polarization corresponds to this, and your LCP is your otherwise called your clockwise polarization is like this, and your RCP is your counterclockwise polarization state. So, any of these polarization states can be, and you can imagine anything else in between is going to be elliptical polarization, right? So, along the equator it will be all these different polarization states. So, it would basically be at this point along the equator it will be linearly polarized, but at 45 degrees this way, and at this point on the other side it will be linearly polarized, but it will be the orthogonal with respect to this polarization, and anything in between is going to be elliptically polarized. So, somewhere over here is going to be more towards the horizontal, and it's going to be left circularly polarized. So, it's going to be something like this, and over here it's going to be once again horizontal, but it's going to be close to horizontal, but it's going to be right circularly polarized. So, that's actually the elliptical polarization that we have, and over here it is going to be closer to the vertical polarization state. So, so you have an ellipse that's looking like this, but that the upper half corresponds to the upper hemisphere corresponds to right circularly polarization state, and the lower hemisphere corresponds to left circularly polarization state. So you will have the same orientation, but it will be clockwise polarization. So all the different polarization states can be represented over here. So why we are doing this? Why are we interested in this? We are interested in finding how the polarization changes. Okay, and first of all, we are interested in understanding if we could manipulate this polarization so that you can change from one polarization state to another polarization state. So it turns out that we could manipulate the polarization, so you can manipulate the polarization state using what are called wave retarders. So what is a wave retarder? Basically it is a birefringent element. When we say birefringence, is talking about two different refractive index, and two different refractive index between the for the x direction and the y direction. Okay, so if you have a birefringent material, then what happens is you could basically change the phase or retard one component with respect to another component. One popular retarder is what is called a quarter wave plate. So what does a quarter wave plate do? It retards by so when you go through that material, basically, right, it retards whatever incoming polarization, the x and y component of the incoming polarization is retarded by as the name suggests, is lambda by 4. That is in terms of the path length, but in terms of phase, you can say that this lambda by 4 implies that corresponds to pi by 2 change in phase. Okay, so if you start with a linear polarization, okay, let's say we are starting somewhere over here, right, and if you actually incorporate a phase change of pi by 2, okay, where let's say along the y direction it is pi by 2 retarded with respect to x direction, then we are talking about moving from this towards this direction, right? So moving from the equator to towards the pole. Okay, so this is actually what a quarter wave plate does. It actually moves you from the equator upwards, or if it's the other way, it is minus pi by 2. If it is plus pi by 2, that means Ey is leading Ex. So in that case, it will go in this direction, right? But if it is minus pi by 2, it will essentially go in this direction, right? So that's what a quarter wave plate does. It essentially introduces pi by 2 phase shift between the two orthogonal polarization components. Okay, so that's what a quarter wave plate does. It moves you away from the equator. But let us look at what a half wave plate does. Right. So what a half wave plate does is actually introduces pi phase shift between the two orthogonal components. So, essentially if you have Ex and Ey like this, if your Ey is flipped, right, so then that actually corresponds to the polarization is still linear, but it would have this would have flipped vertically. Okay, so then that would actually be oriented in this direction. So in essence, what you are doing is you are actually causing a rotation in the polarization. Okay, so essentially what you are doing when you are putting it through the halfway plate is you are rotating the polarization. You are staying in the equator, but you are rotating your polarization when you are using a halfway plate. Okay, so those are the typical manipulation that you do as far as the polarization is concerned. Now this is actually if you want to achieve a particular polarization state, but if you want to use it as a sensor, then things are different. Then what you are really looking for is you start with say one polarization state like this, and you are trying to track and you are sending it through some material which is subjected to some perturbation, and then you are trying to see which way this is moving, whether it's moving this way or along this or along this, along this. You're looking at which way it's moving, and by looking at which way it's moving, you can actually tell what the polarization, what the perturbation has done. The perturbation would have either changed the amplitude. If it's changing the amplitude, then it's only moving along the equator, right? It's just changing it remains over linear, but it's changing along the equator. But if it has changed the phase between the two polarization components, then it would actually move out of this equator towards the poles. Okay, so as a sensor, you are actually looking at the inverse problem. You are analyzing the polarization. So that's what when you come back here, you look at this. What this optical demodulator does is analyzing the polarization state, and you know what you launched into your fiber at the transmitter. You have a specific, you usually put a polarizer here to ensure that you are launching a very specific polarization state, and then you analyze what is the polarization state at the output, and based on the, without any perturbation, maybe it would be the same polarization that's coming out. But if if there was a perturbation, that polarization state would change, and correspondingly this optical demodulator will give a change in the intensity. Okay, so that's how we use it as a optical sensor, and we'll look at that in a little more detail in the next lecture.